In this video, a self-balancing robot is used to demonstrate the interplay of simplex and complex controllers within the ADMORPH architecture to provide guarantees while using high-performance controllers. The diagram shows the conceptual architecture implemented in the bot. It builds upon the well-established simplex architecture that provides a clear separation of concerns. While the complex controllers provide high-performance control but no guarantees, the simplex controller provides high assurance while possibly having a reduced control performance. With that, the approach enables seamlessly switching between the controllers to exploit the high performance whenever feasible but relying on high assurance controllers to ensure system safety when at risk. To realize these switches, this architecture includes three components to manage the switching between the different controllers. The first switch decides on which complex controller to use. For that, it estimates the state of the system and its environment using sensor observations and determines the optimal complex controller to use. Like the complex controllers, the simplex controllers may need to be adapted according to the current state. This task is addressed by the simplex to simplex switch. In contrast to the complex to complex switch, this switch has to provide high assurance that the system is kept safe, not only during switching but also by the simplex controller the system is switched to. The complex simplex switch is the third component. It knows when to use the high-performance complex controller and when to switch to the high-assurance simplex controller. It switches to the simplex controller when the control action of the complex controller is unsafe concerning the current system state and hits back from simplex to complex only if state and control action are deemed safe again. To demonstrate this solution, we use a self-balancing robot. Its safety goal is to maintain an upright position at all times. This safety goal is ensured by simplex controllers up to a certain level of injected disturbance. However, from a performance perspective, it is desired that the robot keeps its baseline position while stabilizing. Therefore, complex controllers have this additional goal, which is achievable by trading off with the admissible level of injected disturbance. The blue tape on the floor indicates the desired baseline position. For visual aid, we mounted 4 LEDs on the robot. Those LEDs are used to show the different execution modes. The upper LEDs indicate whether or not a switch to the simplex controller is necessary to maintain the system's safety. Red indicates that a simplex controller is required to stabilize the system. The green LED indicates that a complex controller can be used. The lower LEDs indicate which controller is being used. Again, the red LED indicates a simplex controller, while the green indicates a complex controller. Currently, the upper green LED indicates that the robot is allowed to run a complex controller. In accordance with that, the lower green LED shows the robot is indeed running a complex controller. What happens if the robot doesn't switch to a simplex controller when required? The complex controller will provide an unsafe value to the motors and the robot will fall down, not meeting its safety goal. That effect is demonstrated in this first phase. Here we can see the robot stabilizing at the marked position and operating with the complex controller as indicated by the LEDs. When disturbing the robot, as we do here by pushing it slightly, the robot can return to its position. However, more significant disturbances cannot be tolerated by the complex controller. The controller fails and the robot falls down, violating its safety goal. As we can see by looking at the LED's status, the complex simplex switch detects the strong disturbance and indicates that switching to a simplex controller is necessary. The upper red LED is lighting up but we force the robot to ignore this signal so that the complex controller remains in charge. This is indicated by the lower green LED. We demonstrate that this complex controller is not able to keep the robot safe when a stronger disturbance is injected. To prevent the robot from falling and to keep it safe, the ADMORPH architecture can be used. Its complex simplex switch will detect unsafe actuation signals from the complex controller and switch to the simplex controller. This controller will then assure safety. This working principle is demonstrated in this second phase. We start again with the robot stabilizing at its initial position at the blue line. As we can see, minor disturbances are tolerated by the complex controller. Now let's inject strong disturbances again. This time, the simplex controller takes over as soon as the complex simplex switch detects unsafe actuation signals given by the complex controller. This is also indicated by the LEDs. Both red LEDs are lighting up. The disturbances force the robot to leave the field of view for a brief moment, but the simplex controller keeps it safe. However, Position control is not provided and is only resumed once the robot returns to the complex controller. With the complex controller reactivated, the robot successfully returns to its initial position. In ADMORPH, we extended this idea to enable contextual adaptations. With complex to complex and simplex to simplex switches, the system can be kept safe in the same way when faced with different situations. We modified the robot to be able of holding an additional weight to demonstrate this adaptability. The robot detects the weight using an integrated sensor. It is equipped with alternative complex and simplex controllers, both designed to compensate the additional weight. The complex controller remains able to provide position control when faced with minor disturbances. When confronted with increased disturbances, the simplex controller keeps the system safe. Then, the complex controller is applied afterwards to return to the position. When placing the additional weight on the robot, the contextual change is detected and a complex to complex switch and simplex to simplex switch is used to reconfigure the system accordingly. During the switching phase, the additional weight introduces a high disturbance such that the secondary simplex controller is used to stabilize the system. The impact of the additional weight can be seen by the inclination angle. The robot is leaning back to stabilize with the additional weight. Once the robot stabilizes, the complex controller parameterized for the additional weight is used. Again, it provides position control. Similar as before, in this contextually adapted configuration, switching to a simplex controller parameterized for the additional weight keeps our system safe when confronted with high disturbances. When removing the weight, the robot detects the change and uses its complex to complex and simplex to simplex switches to adapt to the new situation again. In this demonstration, we utilized a self-balancing robot to show the complex simplex switch mechanism developed within the ADMORPH project. These mechanisms were designed to prioritize high assurance by employing simplex controllers while aiming to enhance performance by executing complex controllers whenever feasible. The set of mechanisms developed in the project enables dynamic adjustments, ensuring that the control action of the complex controller is safe within the current system state. If deemed unsafe, the system switches to simplex controller and returns to complex controller only when the state and control actions are deemed safe once again.